So let's continue with the proof. We had a function which had all those properties, total integral equal to 1, non-negative, etc. From that we constructed a function capital F with the definition, and then we showed that this function satisfies all the 4 conditions of the fundamental theorem of probability. Hence we can conclude that there exists a random variable capital X with CDF given by this F. When I say there exists a random variable X, I mean there is a probability space together with a random variable defined on it with this property. Now, the proof will be complete once I show that this F will have density little f. Now, in order to prove this, I will just write down what is meant by X has density f. This is what we have to show. For any a less than or equal to b, probability that X lies between a to b is the integral from a to b. Okay, now I already know that if I define fx in this way, then this is a continuous function, and I know that X has f as the CDF, therefore X equal to any given value is 0. So I know that I can drop this equality over here. Now this is nothing but fb minus fa. Use the definition of fx. This integral minus infinity to b minus infinity to a. I am just not writing that integrand, this thing over again. So once you do the subtraction you get, and that is exactly what we needed to show. In the course of the proof, we have also learned how to arrive at the CDF from the PDF just by integrating. Now, it is also possible to do the other way around. If you are given the CDF, you can compute the PDF, and you can possibly guess that we have to differentiate this in order to arrive at this one. Suppose you are given this CDF and we plan to differentiate it. The problem with this is that your CDF may not be differentiable everywhere. So you have to have some provision when x is something for which fx is not differentiable. What we do is we just define it to be 0 if the derivative does not exist. In fact, you can define it to be any non-negative quantity. Now you must think that this will always be a PDF for that CDF. But no, if PDF indeed exists, remember not all CDFs correspond to a PDF. For example, if it is a discrete CDF, then no PDF exists. Then of course this technique is not going to work. If there is a PDF, then this must give you a PDF. So if you already know that this admits a PDF, your story is over. But suppose you are given just a CDF, you do not even know whether PDF exists or not. Then what do? You define this function like this and then explicitly check if integrating this will give you back this thing. That is, you check whether fx equals integral from minus infinity to x ft dt, and this must hold for all x. If you find it does not hold, then this thing is not PDF, and if this is not PDF, then fx cannot have any other PDF. So if PDF exists, this has to be a PDF. The decay time of some radioactive particle is denoted by the random variable x. So when you leave the radioactive particle, it will decay, and that will be actually random. So how much time it takes to completely decay, and that is a random variable x, and it has got distribution function this for some constant lambda which is positive. Your job is to find the density of x.